Uh, Hello, welcome back to the continuing lecture in investments. This is Dr. Jeff Hong, and today we are moving on to convexity. And now, convexity is truly a more advanced topic in bond because we have to use um, um, calculus um, to apply to calculate convexity and apply convexity. So first of all, what is convexity? Convexity means, mathematically, basically, a mathematical definition of convexity is um, uh, when, the straight line between 2 points on a curve is always above the curve, the section of the curve that is between those 2 points, right? I mean, this may not uh, uh, this is obviously not easy to it's a mouthful and it's not easy to crack it right away. But of course, everything we are doing is very conceptual, very theoretical, and um, there's you know if you just have if you're a person with just a linear thinking, you can't process it. You should be able to have your mind should be able to process a structural um, thinking, right? The notions have uh, structure. And well, anyway, uh, let me just give you let me show you. This is already very obviously, I know it's threatening, but we all know that the relationship between the interest rate and bond price, right, is a curve like this, right? We all know that. Now, what is a curve? Curve is uh, uh, mathematically, curve is a quadratic equation, quadratic, right? I mean, in this case, um, it's an exponential function, but to be more accurate, it's an exponential function. But you understand the concept of quadratic, right? It's a second order equation, second order. Now, uh, so let me open a. I think I will need a Word file, blank Word file, so we can simply draw on it, right? So let me switch the application screen. Let me stop sharing this and share, just, a plain, you see this is a plane, of course. Now, so if you okay, if you remember, it's very basic, you know, algebra. I mean, function part of the math. Now, if we have two variables, right, x and y, right, and of course, x being the independent variable, x being the I'll just have to satisfy with and y being the dependent variable, right? Of course, uh, something like this is a linear, right? Linear, function. There's a linear, the relation between x and y is linear, right? But something like this is quadratic, right? And so is, right? A curve like this. So in other words, in this case, of course, y is f of x, right? Where y is function of x. So function of x, f of x is uh, alpha squared. I'm sorry, alpha, what am I? Alpha times x squared plus beta x and plus gamma, right? Is second order, right? And of course, depending on the sign of alpha, right? Um, this is quadratic, second order, right? And if depending on the sign of algebraic sign of alpha, right? If it is positive, uh, the curve will be pointing downward. If it is negative, curve will be pointing upward. But let me just use one, now, and of course, in this case, there's no solution for x. There's no solution because the curve is not actually touching x-axis. But the point is, this type of curve is concave to the origin. When you say concave, convex, I'm sorry, convex to the origin, convex or concave, right? If it is pointing towards the origin, right, then it's convex, and the other case would be concave. But also another way to define convex or concave is, let's say we have 2 points on this curve. There's 2 points A and B, right? And if we draw a straight line between A and B, right? And if all the points on this curve, in this segment of the curve, all the points on the segment between A and B. In other words, all the y values of every point, right? All the y values of every point on this segment of the curve, if all of them are below this straight line, then that's convex, okay? So let me switch back to, okay, that's mathematical definition of, convexity. Let's get back to, and now you understand, now you see, I hope, yeah, by now you see this. Our curve, right, it's exponential function, not, quadratic function, but, it's pretty much like, it's quadratic, right? It's in a way, I mean, if you can, it's also an approximation. Quadratic function is an approximation because, for this to become a quadratic function, right, you'll have to extend it very far, and somewhere here, somewhere all the way down, it would have an inflection point. It should have an inflection point. You understand? In other words, if I stretch it all the way, I would have some, it would have an inflection point, the lowest point there, the trough, and then it should go up in a curvature as well. Then that would be a quadratic function. But again, even though this is not really a quadratic function, right? We can approximate that quadratic. We can approximate that curve as a quadratic function, right? Now, what is the reason to approximate? First of all, if this curve is very mild, I mean, the curvature is very mild. If the curvature is here, at least the curvature is, more, pronounced, but there can be if the curvature is like, let's go back to our earlier topic, duration, right? Well, let's think about it. We see, very steep curve, right? I wouldn't, steep curve doesn't seem the right way to call it, but more pronounced curve and less and less pronounced curve. And this curve is almost like a straight line. So in other words, we can, and what was the duration? Duration is the slope of this curve, right? Duration is the basically, the slope of the curve. And that's why I said duration is like, elasticity, right? Duration is like elasticity because the man curve is also an exponential function. With a negative slope, and elasticity is basically what? Elasticity is a straight line of the curve. Slope is a straight line at a particular point, right? A slope is a straight line at a particular point, like this. slope is a specific to this point on the curve. This is not, this is the slope of this curve only at this point where the straight line is tangent, right? Tangent to the curve. But, so there are unique curves everywhere. Unique slopes, or everywhere, right? For example, at this point, that's the slope, but at this point, that's the slope, right? And at this point, that's the slope, right? That doesn't seem right. And at this point, that's the slope. At this point, that's the slope, right? I mean, we have numerous slopes on a curve, right? On a segment, on a curve. So elasticity we are talking about is in general point elasticity, right? Elasticity of demand at a particular point. But think about it. If the demand curve is not this pronounced, but if the demand curve is flat enough, right? The curvature is flat enough to be approximated by that slope, by that straight line. That straight line is, normally, when we show inverse relationship, inverse relationship between price and quantity demanded, price and demand. We use a straight line because a straight line captures the inverse relationship, right? So in elasticity, also there is not only point elasticity, there's also arc elasticity, elasticity of the curve, arc, right? But generally, unless the curvature is very pronounced, right, and the curvature is if the curvature is relatively flat, right, approximation, a straight line approximation is enough to capture the inverse relationship between the price and quantity demanded on a demand curve. Just like that, if the curvature is not that pronounced, it's a straight line, which is duration, right, is enough to capture the inverse relationship between the interest rate change and bond price change, right? Okay, that makes sense. Now, but then again, duration will work pretty well if the this price and interest rate relation curve is relatively flat. If it has a well-defined curvature, in other words, if the curvature is pronounced, duration can no longer predict it, no longer predict the changes well. For example, around here, around this range, right? I mean, if the interest rate changes at most 1%, right? 1% either down or 1% up, the straight line approximates it well. So you can say if the slope is 11.02, right? If the slope is 11.02, and if interest rate changes 1%, let's say interest rate goes up 1%, then bond price will go down by 11.26%. It kind of approximates it, even with a straight line. you can make a relatively good forecast, right? Simply by using that approximation. And if the interest rate goes down by 1%, the bond price will change by 11.26% upward, right? Upward. So this type of, approximation is possible because as long as interest rate changes are relatively small, within, like 1% range, negative or positive, up and down, right? But if interest rate changes, much greater, for example, like -3%, -4%, or +3%, +4%, this straight line cannot give you a accurate price change, right? Because the curve diverges, already from a lot from the straight line, right? So that's the limitations of duration. Okay, in terms of forecasting, if the interest rate changes by small degree, it's a good approximation of, to forecast the price change. But when the interest rate changes by a large degree, it's not going to work anymore. So we need to have a better measure of what? Curvature. In other words, we should be able to approximate this curvature by what? Well, by a quadratic function, right? Because a slope is a linear function, but a curve can be, I mean, if this is curvilinear, it's called curvilinear, actually, curvilinear, right? And it's an exponential function, but at least, for we can, approximate it. We can capture it in a quadratic function and approximate that curvature, right, by a second order, right, a quadratic function. Okay, so that's why that's what the convexity does. In other words, in bond, and you understand why it's called convexity, because it's convex to the origin, right? And all the points, let's say, if you pick the one point here, and draw a straight line between those 2 points, and within the segment of the arc, right, between point A and point B, all the points from here to here, I mean, all the points, between here and here, everything falls below the straight line connecting A and B, right? Now, anyway, so here's the recap of the definition. Curvature of interest rate sensitivity of bond price relation, right? And we know it is, curvilinear, not, a straight line. But the straight line is called duration. You know that. Straight line is called duration. I should have called this Okay, you understand that's the same thing as y in this context. Um, so change in bond price over change in interest rate. That's the slope. Slope is what? Slope is the change over change uh, change in height, change in rise over change in run, right? And the height is the vertical axis is the price, right? And and the run, the horizontal axis is the interest rate, and of course, it's not dollar price. This is actually the percentage, right? We are comparing percentage change. We're taking the ratio between percentage change and percentage change, right? Now, but then convexity is what? Convexity is now the change in duration over change in interest rate. What? Change in duration over change in interest rate? But now let's translate it. What is duration? Duration is change in bond price over change in interest rate, isn't it right? So if you rewrite it by its definition, by the definition of duration, then uh, you can rewrite it this way. But think about it. Taking, if you are, this is basically derivative, right? First derivative, right? Um, change in dependent variable over change in independent variable, or it's also called change in uh, regressant over change in regressor, or there are many ways to call it, right? Uh, but basically, the rate of change, right, with respect to change in another variable, right? That's basically, a first derivative. But you are taking another derivative of the first derivative, so that's second derivative, right? Second derivative. So this is the way to write second derivative, because you are, uh, taking derivative with respect to y twice, right? And so this is basically the concept of convexity, right? Uh, if d is to y, duration is to uh, bond price relation, bond price and interest relation, what elasticity is to uh, you know quantity demanded, change in quantity demanded with respect to change in price, right? In other words, this is, of course, in elasticity, we have to have uh, times, you know what I'm talking about. We have to have, this is not complete, right? You have to multiply that by P over Q. I mean, only then, this is percentage change, right? Changing Q over Q, right? Divided by, changing P over P, right? But, then only then is percentage change, right, in Q over percentage change in P. But, what's important is, the slope. So we're focusing only on, this. So duration is to change in price, bond price over change in interest rate. What? Elasticity is to change in quantity over quantity demanded, right? Over change in price. Makes sense? And just like that, convexity is to change in duration over change in interest rate, right? You remember duration also changes, with uh, uh, change in interest rate. Convexity is to change in duration over change in interest rate. What elasticity is to, right? Change in quantity demanded over change in price. Okay, so we're already out of time. So I'm gonna have to cut the video here and continue in the next video. Okay, so uh, I'll see you guys in the next video. Stop recording.